Okay, let's jump right in by asking a pretty high-stakes biological question. What exactly keeps the trillions of cells in your body from suddenly bursting like overfilled water balloons? Or, on the flip side, what keeps them from shriveling up into tiny, dried-out raisins? Now, I know that sounds a bit dramatic, but this is literally a life or death battle happening inside your bloodstream every single second of the day.
So, welcome to this explainer. Today we're unpacking the Plasma Balancing Act, specifically osmotic pressure. We are going to explore exactly how your body expertly balances water and salt, the mathematical formulas it relies on to do that, and of course, what happens when this incredibly delicate balance goes wrong. Starting off with Section 1, the body's water blueprint. Let's get a handle on our fluid compartments. When you think about it, humans are essentially walking, talking bags of fluid. But this fluid isn't just sloshing around randomly in there. It's meticulously divided. The vast majority of your body's water, somewhere between 55 and 75%, is trapped safely inside the cells themselves. We call this the intracellular fluid, or ICF. The remaining 25 to 45% makes up the extracellular fluid, or ECF, which sits outside your cells, mostly in your tissues and blood plasma. And what's wild is that the cell membrane creates two completely contrasting environments. Inside the cell, it's totally loaded with potassium while actively keeping sodium very low. Meanwhile, the extracellular fluid, like your blood plasma, is the exact opposite. It's high in sodium and low in potassium. This strict separation of electrolytes is absolutely foundational. It sets the entire stage for osmotic pressure. Moving on to Section 2, defining plasma osmolality. Let's look at the golden rule here. Before we go any further, we need to clearly define our core concept, osmotic pressure. Simply put, this is the total concentration of solute particles that are dissolved in a solution. Think of solutes as the solid stuff, salts, urea, sugars, just floating around in your plasma. And here is the golden rule. Water is naturally drawn to areas with a higher concentration of these particles. So the sheer amount of these solutes directly dictates exactly where your body's water needs to go to keep everything diluted and perfectly balanced. Which brings us to a magic window, 280 to 300 milliosmoles per kilogram. This number is your normal blood osmolality. It's the isotonic baseline that your body fights around the clock to maintain. When your blood plasma sits right in this sweet spot, your body fluids are in a happy, isotonic state. The pressure inside the cell perfectly matches the pressure outside the cell, which means water is flowing in and out at exactly equal rates. But how do we actually measure this? Well, to keep tabs on this balance, the medical field uses a specific calculation: 2 times the sodium concentration plus blood urea nitrogen plus glucose. Now notice how sodium is multiplied by 2? That's not a mistake. It's because sodium is the undisputed heavyweight champion of the extracellular fluid. It is the major determinant of your plasma osmolarity. Sure, glucose and urea play a part, but sodium is driving the bus.
Let's hit Section 3, the impact on cells. We are officially entering the danger zone.
Because when those normal ranges are ignored, total cellular chaos ensues. In a state of hypoosmolality, the blood plasma has too few solute particles. So water naturally rushes into the cells to try and balance things out, which causes them to swell up and literally rupture. It's bad news. On the flip side, during hyperosmolality, the plasma is way too concentrated. It acts just like a sponge, sucking water out of the cells, causing them to tragically dry out, shrink, and eventually fail.
And taking the cellular consequence back to a larger scale, you can quickly see how this microscopic chaos translates into life-threatening emergencies, especially for our neurons. If your plasma osmolality drops too fast, your brain cells start to swell. And because your brain is trapped inside a rigid, unforgiving skull, this cerebral swelling is incredibly dangerous. Conversely, if the plasma becomes hyperosmolar too quickly, severe water loss in the brain literally causes the tissue to shrink and pull away from the skull. This right here is why managing blood osmolality is so absolutely critical. Finally, Section 4, regulating the balance. Time to meet the body's rescue squad. Fortunately, our body doesn't just leave all this to chance. We have an automated, highly sensitive rescue squad that kicks in long before our cells explode or shrivel up. And this defense network relies on 2 main mechanisms working in perfect harmony. First, a neural alarm. This is controlled by the hypothalamus in your brain, and it regulates your conscious sensation of thirst. Second, we have a humoral or chemical mechanism. This uses a powerful messenger called the antidiuretic hormone, or ADH, which travels down to your kidneys to adjust exactly how much water you pee out. These mechanisms build into a beautifully elegant, automated feedback loop. Let's say a stimulus like dehydration spikes your blood osmolality. Boom. Osmoreceptors in the hypothalamus instantly detect the change. The brain fires two signals. It triggers your active desire to drink water, and it tells the pituitary gland to release ADH. That ADH targets the kidneys, specifically the distal tubules and collecting ducts, cranking up their permeability. This forces your kidneys to instantly reabsorb water right back into the blood instead of losing it in urine. That extra water dilutes the plasma, dropping the osmolarity safely back down to that 300 milliosmol set point.
Which brings us to the end of our breakdown, and it leaves us with a really fascinating thought to take away today. The next time you eat a heavily salted meal and find yourself desperately craving a massive glass of water an hour later, realize what's actually happening. You aren't just casually thirsty. Your blood plasma osmolarity has spiked, water is actively being pulled from your tissues, and your shrinking cells are sounding a profound microscopic SOS signal straight to your brain. Your body is running complex neurochemical calculations to keep your cellular universe perfectly intact. Thanks so much for joining me on this explainer, and hey, make sure you stay hydrated out there.